All right, here's our week 2 SAT question, and we have ourselves a system of equations: 2x plus 3y is equal to 7, 10x plus 15y is equal to 35. For each real number r, which of the following points lies on the graph of each equation in the xy plane for the given system? And then there's our answer choices. Let's take a look. Before we look at the solution, let's take a look at your results. So out of 104 respondents, you can see the vast majority of people chose answer choice B. It's about 70%, and that just happens to be the correct answer. About a quarter of us, a little bit more than a quarter of us, did miss this question. Now, this is kind of interesting here, that of those responses, the majority of us believed that it was at least a medium level question, if not a hard question. So I'd say medium is about 3, hard is definitely the 5 level here. So I have it on pretty good authority that some of us either straight up guessed or maybe even had the assistance of some AI chatbot working on this question. So don't worry, you certainly have access to ChatGPT on the SAT test. That is a new policy. This is not sarcasm at all. Anyway, here, let's go ahead and take a look at our solution. So notice, of course, that we have ourselves a system of equations. And when you're solving a system of equations, you essentially have system of linear equations anyway. You have 3 possibilities. The first, most common possibility is when your 2 lines intersect at a single point. So here's your 2 linear equations, and they have 1 point of intersection. That is one solution. We call that a consistent system. And I know that that's not the case for this question. How do I know that? Well, because this would be an ordered pair. Like, for example, it would be 1, 7. And if I look at my answer choices, that is not what's happening here. We've got all these r's, these real number r's up in here, and that's not a single solution. Okay, so what else do we have? We have the possibility of one of my lines looking like this, beep, and then the other line looking, almost exactly like that, except for in a different location. These things are parallel, and if they're parallel, they never intersect. If they never intersect, you have 0 solutions. We'll call that an inconsistent system. And, well, that's not the case either. Why is that not the case? Well, if they do not intersect, there's not going to be an ordered pair that represents a point that works in both of the equations. So that's not it either. So what is our third possibility? Well, our third possibility is a really silly one, and it goes like this. Here's your first equation when you graph it, and the second equation when you graph it, it's it's right on top of the other one. And you have infinitely many solutions. In this case, infinitely many solutions. There's an I in there someplace. And we call that also a consistent system. But unlike this one over here, which has only one solution, this is a dependent consistent system. And this is what we're looking at. Now, if you look at your original equations here, these 2 linear equations, we could get that right off the bat by noticing that the second equation is just the first equation multiplied times 5. So for example, if I just take the first equation, multiply everything by 5, I would get 10x plus 15y is equal to 35. Well, there you go. So again, if you were to graph both of these, hey, why don't we graph both of these? And we can see that play out on Desmos, and this works. So it did put them into a standard form, which is okay for the SAT version of Desmos because it'll accept it. It was, I don't remember, so I'm going to have to take a look again. It was 2x plus 3y equals 7. 2x plus 3y is equal to 7. So there's your first equation, and then you go to graph the second one as, remember it was all times 5, so it's 10x plus 15y is equal to and 35, and oh, look at that. So you can't tell the difference. If I turn this blue one off and turn it back on, you can see it's exactly the same graph. So there you go. Yeah, so maybe that part was obvious to everybody who took this, every single person, I don't know. Let's see how we're supposed to select between these answers. Now, what they've basically done on here, what the fine folks at the SAT at College Board have done is that they have parameterized, let me write that word down, parameterized or parameter. Here, look at this. Just look at this. Just listen to this. It's right here.
Parameterize.
Yes, exactly. You can see describe or represent in terms of a parameter or parameters. That's essentially what they did. Now, we've done something like this in our classes whenever we have written an equation in terms of some other variable. What they have done is that they have written their solution in terms of R. In terms of R. What the heck is R? R is just a number. This is a real number. Those are all the only kind of numbers that you know up until this point, probably. Anyway, so here's what I want you to notice. I want you to ignore the first one because the first one is straight up wrong. How do I know it's wrong? Because it looks unlike the other ones, and this one's complete garbage, as we're about to see. But if I look at B and I look at C and I look at D, there's something that I can notice in each one of these. Notice that on B, this is the same thing as the y coordinate. So essentially, this one is as if it is in terms of y. I'm going to say that because that R value, which is what each one of these ordered pairs is in terms of for real, is in the y position. And then likewise, if I look at the other two, these ones have the R in the x position. It's the same thing as the x coordinate here. So these are as if they are in terms of x. Okay, well, now that we've got that understanding under our belt, let's see how we would actually write these. So I'm going to take this top equation. You could take the bottom equation. It doesn't matter because they're both the same equation. I'm going to take the top one because it's kind of reduced. And then also notice that like in these B, C's, and D's, all of these answer choices have these numbers in it. The only one that doesn't is answer choice A, which we're throwing away. It has the little 35 in it. Okay, so what I'm going to suggest doing is picking one of these things. Let's say we pick answer choice C and let x equal R. So watch. Let x equal R. So I'm going to take my equation here, which was 2x plus 3y is equal to 7. And we're going to take out our x value and we're going to substitute it with R. And then we're going to solve the resulting equation for y so we can see what the y coordinate is supposed to be. Okay. So whenever I go to solve this, well, I got to do my substitution first. So 2r plus 3y is equal to 7. I'm solving this thing for y. And the reason why I'm solving for y is because I already know the x coordinate. It's r. I just need to figure out if this is the true y coordinate or perhaps this one is the true y coordinate. I'm going to do that by, like I said, solving this equation for y. It's going to be y in terms of r. Okay, so I'm going to take this 2r, I'm going to subtract it to the other side. I'm going to subtract it because currently it's being added to the 3y. So I have 3y, that should be blue. 3y is equal to negative 2r plus 7. And then I need to get rid of this 3. It's being multiplied times the y, so I'll have to divide it over. I'm just going to essentially divide everything by 3. So I'll have y is equal to negative 2/3 r plus 7/3. Okay, well that sort of looks like what these answer choices look like. So let's see if this matches up with either C or D. So this one is a positive 2/3, but I had a negative 2/3, so I know it's not that one. So this one goes away. And then, well, here, let's look at D. It does have the negative sign, but it has division by 2 instead of division by 3. Very, very clever. Okay. That I'm thinking my answer choice is actually B. So let me show you that it is actually B. So this time, whenever we do this same exact process, we're going to let our y coordinate equal r, because you can see it's in the y position. So let's try that. Let y equal r. And then we're going to do the same exact thing we did before. 2x plus 3y is equal to 7. We're going to take this r value here and substitute it in for the y. And then solve it for x this time. So 2x plus 3r is equal to 7. Why am I solving this thing for x? I am solving this thing for x because I already have assumed that the y-coordinate is r, and we want to see what the heck this thing is. So I'm going to subtract over the 3r. So I have, once again, 2x is equal to negative 3r plus 7. And then I divide by 2. X is equal to negative 3 over 2r plus 7 over 2. So hopefully this looks exactly like answer choice B. Does it? Let's see. A negative 3 over 2r, yes, and also plus 7/2. So that is, in fact, the answer. Okay, so when I first saw this question, I was thinking, man, Desmos wouldn't be much help on this at all, would it? Other than understanding that it is essentially the same equation. And then I got to thinking, actually, Desmos could solve this thing for you. Watch, I'll show you how. Basically, all you do is you just type these things in, just like you see them. Even with the r's, even with the parentheses, even with the little comma, you just straight up type it in. So I'll show you that this is the correct answer choice by actually typing in on Desmos. And I did check it. It works on the test version, the SAT, PSAT test version of Desmos. So we're all good here. So I'm going to open up my parentheses here. And inside of it, it was... I don't remember. I think it negative, was it 2 over 3 or 3 over 2? I don't remember. Let's see. It was negative 3 over 2. I guess I could have just looked at the equation and solved it in my head. Negative 3 over 2r. 3 divided by 2. Get out of that, and then r. I need an actual r over here, so I need to go to the alphabet and do an r. And it says add slider, and we definitely want to, so I'm going to click that. Come back up here, and I still have more plus 7/2, I believe, plus 7 divided by 2. And then I need to arrow out of that, and then a comma, and then an r. And I'm going to actually label that point so you can see it happen. And now I can move my little slider, and you can see that. Ooh, look at that. It goes up and down on that exact line. And so you could have put each one of those things in there and then just check to see which ones line up on the line that you actually have. All right, so I'm going to actually extend this just a little bit and examine specifically answer choice A. So I'm going to go ahead and type in answer choice A here, just like I did on the previous one, the actual answer, and show you what happens here. So on this one, I don't remember. You know what? I'm just going to side by side this so I don't have to keep flipping back and forth. All right, so this answer choice for A was r divided by 5 plus 7. Okay, and then comma, and the next one was negative r over 5, so negative r, back over here, r divided by 5, arrow out of it, and then it's plus 35, so plus 35. Okay, let's full screen this again, and I don't see it. Here, let's zoom out. Oh, there it is. And maybe I even label this one too. It's controlled by the same R value here, so I can move this and I can see it's definitely not on the line. So maybe you're curious as to what line that actually is on. Well, I'm going to extend this a little bit and teach you something about what we call parametric equations, because essentially that's what these things are. So parametric equation basically takes a curve and describes the x-coordinate and the y-coordinate in terms of some other variable, which we call a parameter. Now, the most common parameter that people use is t. This one just happens to use r. It's whatever. And I'm going to basically rewrite this thing. Actually, so I don't have to keep scrolling. I'll just copy that, bring it down here. Boom. I'm going to rewrite this so that you can see what I exactly mean by parametric equations. So this first one here is my x-coordinate is equal to r over 5 plus 7. And then over here, my Christmas colors, my y-coordinate is equal to negative r over 5 plus 35. Okay? Now, I can do what's called eliminating the parameter so I can get it back into a traditional equation with just x's and y's, gets rid of the parameter r. And essentially what you do is that you just solve for your parameter in one of these equations, it doesn't matter which one, and then you can substitute it into the other one. So I'm going to solve for the r over here in this x equation. I'm going to have to subtract over the 7, so x minus 7 is equal to r over 5. Now, ordinarily, I would multiply by 5 over here, but notice what I have in the second equation. It already has r over 5. There's a negative sign in front of it, but that's okay. What I'm going to do is I'm going to take this x minus 5 and substitute it in the place of r over 5 because it's the same thing. So I have my new equation as y is equal to negative x minus 7 plus 35. Distribute your negative sign. Y is equal to negative x plus 7 plus 35. And then if I'm going to put it back into standard form like everything else was, add the x over, combine these, and I believe that's 42. And you can see that's definitely not the same equation as the other equations, but I'm going to type that into Desmos so you can see what's what. So if I go down here to the next line, it was x plus y is equal to, and 42. Boop. And you can see the line goes through that point. Not only does it go through that point, but when I move this parameter back and forth, boop, 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 it stays on that line. So the way that I just did that, eliminating the parameter, we could have done that in order to find our solution from the very, very beginning. In other words, if I had taken this answer choice again and eliminated eliminated the parameter just like I eliminated the parameter before. Oops, that did not work. Here, let me hit undo, paste image. Okay, that works now. If I do it exactly the same way that I did before, we'll say that this thing right here is our x is equal to negative 3 over 2 r plus 7 over 2. And then for the other one, y is just simply equal to r. So notice that there is a r in the first equation. I can just basically take it out and replace it with y because it's the same exact thing. And so my new equation becomes x is equal to negative 3 over 2 times y plus 7 over 2. And now, in order to get it into standard form, so it looks all nice and pretty, we'd multiply everything by 2, and I'd get a 2x is equal to negative 3y plus 7, and then add your 3y over to the other side. 2x plus 3y is equal to 7, and that looks super familiar. Now, these things called parametric equations, you may not see them until pre-cal. We also deal with them in calculus. And what parametric equations do for us is it gives us a way to represent a curve when it's really hard to write the equation for it explicitly. These these are really kind of a corny way to write each one of these linear equations because it's very easy to write a linear equation. But here, let me show you a couple of super crazy parametric equations because we have this up and Desmos has the capability of doing it, but it insists on everything being in terms of a parameter t because, like I said, that is the most common one. So I'm going to turn all this stuff off. Go away, go away, go away. And let's come down here. And then here's our first one. If you wanted to type this in two, oh, I need to turn off these labels too. You want to type these in two so you can play around with it, you can. So you want to open up your parameter, your parentheses here, and you basically are typing in your parametric equations as if it's an ordered pair, but unlike the one that we typed in, we're not going to use R, we're going to use the parameter t. So this one starts with, in the little functions here, sine, which we will learn about in a future lesson. So I'm going to do sine of t. And it says add slider. You don't add the slider this time. So get out of it, and then a comma. And the next one is going to be sine of 10t. So sine of 10t. 10t? Boop. That's a y. Try again. T. There we go. And that doesn't look like it did much, if anything at all. So I need to change what this t goes up by. So I'm not real sure. So I'm going to change it. It's like the domain here. So I'm going to change it from negative 100 to positive 100. That should have it covered. And it just looks like a square, but it's not. Because watch what happens whenever I zoom in here. Are you ready for this? Are you ready? Wow. There's no way that you're going to be able to get yourself a regular, good old-fashioned, this is not even a function, right? So you couldn't get a function that's going to represent what this curve looks like. Okay, I've got one more for you. Let me turn this one off, and then I'll show you something kind of cool on the internet. So here's the next one. It is a t plus and sine of 5t. I wish they would put a t on here because, I mean, if they're using this thing as something that's capable of doing parametric equations, it'd be nice if it was just right there on the default keypad. Anyway, so t plus, and this one's going to be sine of 6t. So t plus sine of 6, and then go back over here to t. All right, well, that looks a little weird. I need to change this parameter a little bit, and let me kind of zoom in. Zoom. Okay, so let's do I'm going to do the exact same thing again. I'm going to go from negative 100 to positive 100. Whoa, look at that. That's crazy. All right, and maybe you can zoom in. It almost looks like cursive, right? Somebody's writing cursive across your screen. What a crazy looking set of parametric equations. All right, and just one last one. This one's interactive. Link will be in the description. Actually, it's not. But you can just search it up. It's called The Art of Parametric Equations. And this one has some sliders here, and you can see what the parametric equations are up here in the corner. Cosine and sine, those are some more of the trig functions that we'll learn about towards the end of the school year. And these little sliders on the left and right, you can kind of change them and see the cool kind of things that these parametric equations will do whenever you change the parameters. Really, really, really interesting. Okay. Or should I say really beautiful because it's art. All right, so that should draw to a close all this parametric. Wait, let me see this word again. Actually, let's have the internet say it again.
Parameterize.
Yeah, exactly. Of a couple of linear equations on the SAT.